Now I think it's 1 minute past 6 p.m. Central European time. I think we can start slowly but surely. Welcome everybody to the webinar today. We have a very interesting topic today. We have thermal energy storage with phase change materials and fundamentals, applications, and example in ANSYS Fluent application. So I would like to start with the sort of rules for the webinar. I would like to ask you to turn off your cameras, turn off your sound, and all of your questions you can write in the chat. We have a chat, and we will go through those questions after the webinar or at the end of the webinar, let's say. And we have also prepared a survey, a poll with the question to better understand your level of expertise, your knowledge of the tool and of the topic. So I would like to ask you also to go through that voting and leave your comment there. And I would like to start with a brief introduction of WiredWhite, or tell you a little bit more about WiredWhite, what we do and why we do it. So we are a platform, an engineering platform, educational platform. We envision our network as a platform that guides individuals through the entire process of their growth as an engineer. We see our role as a sort of enabler by bringing customers on one side and partners on the other side, technical experts on our platform. And we are providing also absolutely necessary tools to achieve a brilliant cooperation between those two, between customer and partner. And why we do it is because of our vision or our mission to accelerate and optimize the diffusion of electrification worldwide, because we believe that this is possible through enablement of the global cooperation, giving customers and partners the space to cooperate, to collaborate on our platform, and to share the knowledge. And that is why we providing this platform for these sort of activities for that sake. And today's speaker is Süleyman Nisanoglu. Süleyman is a mechanical engineer with over 11 years of experience. He has a professional experience in academic and practical one. And he has a background in thermodynamics and computational fluid dynamics, CFD analysis. He holds a master's degree, and his research focusing on CFD analysis for PCMs and PCM integration in solar energy systems. And he further deepened his experience throughout his doctoral research on this topic, on thermodynamic cycles. Süleyman is proficient and advanced in simulation tools, primarily utilizing ANSYS Fluent for the CFD analysis. But beyond that, of course, he uses beyond the commercial software his own sort of scripts and tools. And he has demonstrated a profound understanding of numerical methods by developing and implementing his own finite volume codes in MATLAB. He has done this for his academic research, for his PhD thesis, and his core areas of expertise include numerical methods, differential equations, energy management, and hydrogen energy. And now I would like to pass the ball to Süleyman to go through the material and to get to know that topic on the PCMs. Please, Süleyman. So yours now.
Hello and welcome. I will share my screen. Could you see my screen?
Yes, we can.
Super. I will begin today's presentation by discussing energy definition, followed by an overview of energy source with a focus on renewable energy source. Then we will delve into solar energy and subsequently concentrate on concept of energy storage. This is critical because of we want to use solar generated energy even when the sun isn't out. Energy continuity is incredibly important to us. After that, we will continue by explaining thermal energy storage method and examining different type of PCM, fast change material. I will especially touch on domestic application of PCMs and then when explore fast change using ANSYS Fluent. We will even do demo together. Okay, may I start the presentation? One minute. Everything is fine, I think. Okay. Energy is indispensable requirement sustaining life and continuing human activities. From daily life to industry, energy is needed in every area. However, our energy resources are not unlimited. And energy can exist in many forms, such as thermal energy, mechanical energy, kinetical energy, potential, electric, magnetic, chemical energy, and nuclear energy. The total of these forms is very important, of course. However, each form differs in how easily it can be converted and used efficiently. The world's main energy sources have traditionally been coal, oil, natural gas, and nuclear energy. However, these sources are significant criticism due to environmental impact. For example, fossil fuel cause climate change due to carbon emission, with nuclear energy poses threat through radioactive waste and accident risk. Therefore, two primary ways to use solar energy: first of all, photovoltaic system. Photovoltaic panel consists of semiconductor surface that converts sunlight direct into electricity. Another one, solar thermal system. Solar thermal system, the right one, solar thermal system collect solar radiation and heat a fluid, making energy usable in thermal form. Water is usually primary fluid used in this system. We will focus on solar thermal system. The biggest issue with solar energy is that it is intermittent. It's only available during the day, and its efficiency decreases on cloudy day or during winter. This creates the necessity of storing energy for times when it cannot be used directly. The timing of energy supply and demand rarely match. For instance, energy production begins as the sun rises, while human energy demand peaks in evening. To bridge this gap, thermal energy storage have been developed. These systems allow energy collected during the day to be stored for use at night. Solar energy collected during day for nighttime use makes sustainable use of solar energy possible. One of most common method is storing thermal energy. One of the basic form of this storing energy in liquid. Yes, water is commonly used in this system. However, liquids like ethylene glycol or some alcohol, which have lower freezing point, can also be alternative of water, of course. Liquid energy storage is widely used in solar water heating system. However, drawback of this method is the occurrence of heat losses both inside tank and during transmission of water. Not only liquid, but also solid material can be used for heat storage. This method especially preferred for building low-cost and long-lasting system. A commonly used material is gravel. A fluid, such as air or water, is heated by pass through a heat source and direct to the area containing the gravel, this small stone. This method operates through convection. As the heated air passes through the gravel, it transfers its energy to the stones. These systems are generally used in large facility where there is high demand for hot air. Another energy storage method is seasonal energy storage for long-term solution. After 10 or 20 meter underground, temperature are no longer affected by seasonal change. Therefore, the underground can act as a natural energy in rock. Especially pipes are placed into drilled channel for this method. The heat transfer fluid circulating in this pipe, and when needed, this energy can be brought back to the surface for use. This system, that's very important for me, this system can also be integrated with heat pump system. And chemical energy storage, that is another method. Energy can be stored not only through physical change, but also chemical bond. The energy in chemical bonding relates through exothermic reaction. Gases commonly used in this method include ammonia or hydrogen. Hydrogen gas obtained from water through electrolysis. It can be stored, transported, and burned with oxygen to release energy. The combustion process is similar to natural gas, but the only byproduct is water, without carbon dioxide, of course. This cycle formed the foundation of an eco-friendly energy system. This system also is popular. And last one, fast change material. One of them is organic fast change material. Organic fast change material are most commonly used group storing heat during fast translation. These materials are particularly suitable for low temperature application and have wide range of melting point. They are widely used in solar energy system, especially residential hot water production. The most well-known organic fast change material are alkanes, such as paraffin, and fatty acid. Alkanes have chemical formula carbon and hydrogen, 2 times N plus 2. While fatty acid, the material are abundant in nature and relatively easy to synthesis. One of the biggest advantage of organic fast change material has high chemical stability, making them resistant to repeated heating and cooling cycle. Additionally, they do not undergo unwanted fast separation during melting and freezing. Typically, melt between 35 and 70 Celsius. Paraffin also low cost, non-corrosive, and non-toxic. Another fast change material is inorganic. Inorganic fast change materials mainly consist of salts and salt hydrates. These materials operate a wide melting range, such as 10 Celsius to 900 Celsius. Their stability at high temperature makes them indispensable in many thermal energy storage systems. The major problem in the major problem with inorganic fast change material is their tendency to supercool. During solidification, these material may not solidify even when the temperature drop below the fast change point. That is problem. And third type of the fast change material is metal and metal alloy based fast change material. Metal and metal alloy can also be used as fast change material. However, due to low latent heat capacity, their using areas are limited. For low temperature application, cesium, gallium, indium, bismuth are used. Fast change material are used in wide range of fields. For example, industrial system, fast change material can be placed around large pipe heat exchanger to store thermal energy, such as wax-on is product of NASA. The energy of hot fluid flowing inside the pipe is absorbed by the surrounding fast change material and stored for later use. Fast change material integration is also possible in residential solar hot water systems. A PCM tank placed top of the cylindrical water for energy storage. Alternatively, spherical container filler with PCM. Energy storage system are not limited into tank application. As shown in diagram, a heat storage unit can be placed before the hot fluid reaches. We will make demo with this heat storage unit, this blue one. This is especially useful in continuous flow system to balance temperature fluctuation of the fluid. In daytime, after that discharge in nighttime is this step. Design is critical in such system. Parameters like material type, PCM quantity, heat transfer area, or fluid velocity directly affect system efficiency. Therefore, engineering design should be supported by experimental data and before computer-aided analysis such as CFD. The performance of PCM strongly depend on operating condition. For example, a PCM, the gray area, whole gray area is PCM and blue is water pipe. For example, same system with PCM that works well in hot country like Spain may not perform similarly in colder country like Germany. This is due to a mismatch between PCM melting point and the average of operating temperature. Determining the correct melting point is critical for system efficiency. Every country, every climate has own melting temperature. Therefore, we must find, using CFD, appropriate melting point. Therefore, before installing system, region-specific temperature profile, fluid velocity, and use habits must be considered. Otherwise, incorrect PCM choice may lead insufficient energy storage or inefficient operation. The right material stores maximum energy under the right condition, ensure a sustainable system. We know that, we know that total enthalpy, total energy is constant. pointer here, yes. Here, total enthalpy is function of sensible enthalpy and latent enthalpy time F. F parameter is liquid fraction. Then enthalpy changing in the time is here. That is total differential equation for us. We consider in Fluent this differential equation. In cylindrical coordinate system, our energy equation is here. Actually, both equation is same. K is thermal conductive coefficient. Rho is density. Cp is heat capacity. And this L is constant number of latent heat, solidification to melting energy. Then last formulation is here. The function of fast changing point here. Because of insensible heating, we only consider here this part or this part, but at changing phase, only liquid fraction, this term is changing and temperature is constant. Of course, we know when changing phase, such as water boiling or freeze melting, the temperature for pure matters is constant. Yes, now we can continue with ANSYS Fluent. Yes. 1 minute. Here, this is software, ANSYS software, and we can select analysis system. Also, we can select component of system. First of all, we need to create geometry. Workbench, here, first we open the workbench program, this program, writing workbench, and select ANSYS Fluent. Here, fluid flow Fluent. And here, ANSYS Fluent uses discretization method called the finite volume method, convert the differential equation into algebraic expression, then solve them. Now, let's create our geometry. I will be using design modeler for this. Of course, there are newer drawing program available, of course, but I am a bit old school. Still, I recommended design modeler. It generally doesn't cause many issues. Right-click and select design modeler here. Design modeler, Alt-1. After that, space claim, and very new is discovery. I prefer design modeler, but I suggest discovery, of course. But I right-click and select design modeler. For the geometry creation, I hope ANSYS will open quickly. Very nice. Here, I will draw a rectangle. Here, the short side of this 1 minute. Look, I click look at for XY plane and click new sketch. select this sketch and here sketching. Also, I want to change unit meter to millimeter. Yes, I will draw small demo. Therefore, I will draw a rectangle here. The short side of this rectangle will represent the radius of pipe, and the long side will be length of the pipe. I am optioning for two-dimensional analysis for the sake of speed. This will be time-dependent analysis as I want to observe the effect of time, especially to see melting process over the time. So, well, perform two-dimensional analysis, but we need, of course, three-dimensional pipe to ensure the results are compared to three-dimensional pipe. We will utilize the axis symmetric feature. Here, this part is axis. You might recall from the analysis class in university that integrating an area in radial direction give us the volume. The program, ANSYS Fluent program, handles this for us. Well, we will select this option, axial symmetry option, within the program after the meshing stage. Okay, we can draw this geometry. This part is half of the pipe. Click dimension and give a radius of this one, for example, 15 millimeter radius of the pipe. And click concept surface from sketch and select this sketch 1. And here, this operation must be at frozen because of pipe is a fluid material. Inside the fluid material, water. After that, I will draw fast change material part, fast change material body. Here, name is, click rename, water body. Maybe we can add fluid water body, okay. Then click XY plane again and new sketch 2. And we can create another rectangle like hollow cylinder. That is PCM, fast change material. Five millimeter fast change material. Okay, we can select 10 millimeter. Okay, 10 millimeter. Anyway, not important. Again, surface from sketch and select sketch 2. Add material, no, we select add frozen. Generate, okay. Fluid, PCM body. And little trick for this system, I select both of them, click Ctrl K on keyboard, and form new part. Because of this, we don't consider conduction, contact element. We don't consider contact element. Everything make automatically using this trick. Okay, we close this geometry. After that, mesh. Meshing can be defined as process of dividing a physical domain into smaller subdomain or elements. The primary goal here is to simplify the solution of differential equation. The model is divided into smaller elements. I hope mesh is open, meaning the model is meshed. The key is to determine the most effective way, subdivide the model into smaller pieces using chosen elements. I will using sizing and phase meshing. I want the mesh to be denser near the edge so I can apply bias. The near of the edge must be fine, more fine mesh. Okay, very nice. Using sizing and phase meshing. First of all, sizing. Insert sizing. I select, click here, edge, all horizontal edge. Okay. Type is element size. I'll change number of division. For example, 400 division, very nice. And again, I select sizing for water pipe. Number of division is 60, but I want to mesh to be denser near the edge. Bias type is here. Small, long, small. Okay, here. Bias factor is 1.2, for example. Okay. And in other PCM side, I want the PCM side equal mesh sizing. Number of divisions, 60, okay. Also, okay, everything is good. I change here the quality for mesh. Smoothing is high, but that is not important. We can generate mesh. This result is worse, not good, because of we don't make phase meshing. Wait, please. Until here, could you have any question? The result is not good, not perfect. No, any question? Or here? No, okay. And we can click phase mesh, phase meshing, and generate. The mesh is good, I think. Yes. Good. Finally, we will name inlet outlet was the PCM. Here, this one is named selection inlet, velocity inlet. Here is outlet. We write outflow. Okay. Here, axis. And this part is convective boundary condition. Convection wall, convection. Okay. Then we can open the Fluent. Actually, everything is finished. We only maybe maximum 5 minutes we can handle the Fluent. Because of the important thing is correct geometry and correct mesh. Another step, nearly same. We select fluid flowing type. This one is turbulence or laminar. And first of all, when we open the Fluent program, it asks us how many processor core we want to use. Here, processor, I select 4. For student version, maximum 4. Let's set our core count. Also make sure check double precision option here. This means program will consider 16 decimal places after the comma instead of 8. During the fast change, a concept called liquid fraction, which is the ratio of liquid mass to total mass. The liquid fraction change very, very slightly during the fast change process. So 16 decimal places help us to get accurate result. We are performing transient analysis. Transient analysis meaning depend the value change with time. Here, transient analysis. Also, for axial symmetry, we want to use integral of the result rather than just flat representation. Select axial symmetry. Very nice. Let's select our material here. Viscose type is laminar. I will give very small velocity inlet. And of course, we must calculate Reynolds number first of all, but I will give very small inlet velocity this time. Energy equation is on, and solidification and melting is on. Okay. Then material. We must add material here. Fluent database, water liquid, and I will change this silicone. I change the silicone as paraffin. Here. Okay, water liquid is good, but I change this material. 1 minute, I will find the image as here. Material properties. Density is different. Solid and liquid density is different. We change here. Piecewise linear. 44 Celsius. 44 plus 273. 317 Kelvin. Okay. First of all, this point is not important. Not 0 Kelvin, of course. 0 Celsius starting for the density value. 244, the solid density is 930. 930. Point 2 is fast change temperature. Maybe we can write that 99 is same value. And point 3 is comma 0, 1. Now phase is liquid 830. And 0.4 is not important, anything you can write. Here. This point, 317, is fast change, solidification or melting point, and density is change, solid and liquid density. Okay. Heat capacity is constant, not change in solid and liquid, is same. 2.1 kilojoule over kilogram Kelvin, we write constant. But unit is joule, we write 2100. Thermal conductivity is same. Solid and liquid. Viscosity not important for this case. Latent heat 190,000 because of joule. This unit is kilojoule. Solidus temperature and liquidus temperature. Okay, we create paraffin. Change, create, yes. Very nice. Then, in cell zone condition, we will assign this material respectively area, water region as liquid water and PCM region. Here, PCM body is paraffin, not air. And water body is water. Additionally, we will input our condition in the boundary condition, such as wall temperature, water inlet temperature here, boundary condition. Velocity inlet, I don't know, maybe I will make mistake, but 0.01, 350 Kelvin, and convection heat transfer, the outside the wall, convection, heat transfer coefficient 20, free stream temperature, I think 300 is good, okay. Another one must be outflow, here outflow, axis is axis, okay, everything is good. Cold system 300 Kelvin and water is 350, and the solid PCM must be changed fast. Finally, let's the solution algorithm to simple meaning semi-implicit method. Here, solution method, simple, okay. And normally I use Presto for converge, but this time we use second order. Now this is demo. Okay, and we click patch for initial condition, initial temperature, 300 Kelvin. Everything is 300 Kelvin. Everybody is 300 Kelvin. Number of time step is 999. Time step size is 0.001. Time step size must be very small. Maximum iteration is 2000. Maybe 200 for this demo, and click calculate. And very long time we must be wait. Because of our time step size is very small. but solution is converted. Of course, we will not wait to 2 day or 5 day. My master thesis was 25-day analysis. During the analysis, 25 days. Anyway, we can stop the analysis. Very nice. We can see solidification and melting. Liquid fraction is very small region, of course, very small region. Here, can you see? This is starting point of melting. And we can check the temperature also. Here. Yes. Thank you for listening. Dimitri, I can close my screen.
Yes. I will just quickly ask if we have any questions from the room. So you're free to ask Suleiman any question. If something was not clear enough or you have any specific question to your topic or to your subject, it's the right time now to ask. We'll just wait for another minute maybe, and maybe we will have some questions arrived.
Yes, I have a question.
Yes, please go ahead, Palu.
Yeah, so as you had earlier said, we should also consider the on-site parameters, the environment parameters when we have to match the PCM conditions along with the environment conditions. So how will you consider the parameters when you're simulating it in the CFD? What boundary conditions could you give?
I think it's depend on your analysis. We can, first of all, we must, in real system, we must validate our analysis. And for example, we must find an article or experimental system. After that, the experimental system corresponding environment conditions such as convection coefficient, for example, convective heat transfer coefficient nearly must be 24 outside, nearly around to 10 watt over meter square Kelvin is inside the laboratory condition. But of course, we need to calculate, and before the analysis, we can get this information.
Okay. Thank you.
My pleasure.
Anyone else? Guys, someone has a question? Or ladies?
Question?
Yes, please, Daniel.
Yes. We just saw through the simulations, and I would like to ask a question regarding the results. So basically, we chose certain parameters, say for example, convective heat transfer coefficients and all. But however, at the last, when we analyze our results, say our simulation results, what are the parameters that we are going to consider? For example, I have certain experience in aerodynamics, CFD in aerodynamics. So if we simulate airfoil, simulation with CFD airfoil, we consider drag coefficients or lift coefficients and so on. And for this type of simulation, what are the main the simulation results or parameters that are that are taken into consideration, and how are these parameters gonna influence our research? And as well as I also wanted to ask, after these simulations, after we run these simulations, how are we validating our simulations, and do we have any open source experimental data, or how are we gonna validate that? That is my question.
Actually, very good question. First of all, the parameter for the validation is liquid fraction. Liquid fraction changing in time is very critical and characteristic for fast change material calculation, and we must show in our article, scientific article, fast change material liquid fraction changing in time, and this changing must be a good relationship with open literature result. For example, Salomon 1984. I remember Salomon 1984 is very good example for validating for ice, melting ice, because of water or ice is very fundamental of us. Also in mathematical model, Stephen two-number problem. Solution of Stephen two-number problem is exact solution of this simulation. You can also verify your result. For Cartesian coordinate. Also cylindrical coordinate, we have no mathematical solution. Actually, I tried long time ago the mathematical solution, an exact solution for cylindrical coordinate, but I can't. I hope one day I can. But now we have for Cartesian coordinate, Stephen two, no problem. Okay.
Yes, and the resulting parameters, for example, the fluent results that we consider, what are the monitors that we are considering, like the monitor parameters that we are considering?
The monitor parameter is liquid fraction.
Okay, all right.
Yes, you in using Fluent, you can get the liquid fraction changing with time, like drag coefficient in aerodynamic or lift coefficient.
Okay. Mm-hmm. Yes, thank you very much.
My pleasure.
Yeah, thank you for that question. Anyone else? Someone would like to ask from his domain or from his specific application something? I think that's the best time to do that, since we have our expert now in the call, and you can ask whatever your current issue is with the CFD analysis or with phase changing materials. So it's a good opportunity, I would say. If it is not the case, I would just switch to the last slide that I have. For today, I would like to briefly introduce you our special code, discount code for any purchase on our platform. It's called WiredWhite 10. So after the webinar, you can enter this discount code and order any course that you would like to purchase, or any tutoring session, also with Suleiman as well. And you can get a discount of 10% for that. So you can find all the materials under courses, WiredWhite.com, and WiredWhite.com/members. You can book a session with Suleiman to go through your specific problem, specific issue with the CFD analysis. After the webinar, we will, of course, share those slides that were presented during the webinar by Suleiman And we will also share the video that we have recorded during the webinar. So you can also get back to that afterwards offline and look through that again. Look through the through the slides, through the material, and use those equations or use the theoretical background for your study or for your research. So last chance to ask the question. Any question that you have related to the topic? If not, then I would like to thank you all for participation, for your time, and for joining the webinar and going through those materials, through those slides together. So thank you so much, guys and ladies and gentlemen, and we will see you again. Looking forward for the next webinar. In 4 weeks, we will have another very interesting topic. I think from that CAD, computational aided design, and I'm looking forward to that as well. So see you guys next time, and take care. Thank you again. Bye-bye.